Hello everyone, I am Sriram Ganapati Subramanian, here to present our ICML 2024 work titled Confidence-Aware Inverse Constraint Reinforcement Learning. I would like to start with a quick introduction to reinforcement learning or RL. RL has two entities, an agent and an environment, where the agent's goal is to maximize its cumulative discounted sum of rewards. The agent is learning an optimal policy which provides the best action to perform at each state. In many real-world environments, it may be more convenient to define constraints in addition to rewards. These are constraints that the agent needs to satisfy for the reasons of safety, comfort, or aesthetics. Hence, the constraint reinforcement learning or CRL paradigm has been introduced, where the agent also receives a numerical cost associated with its action in addition to rewards. This cost corresponds to a finite set of constraint functions in the environment. Here, the objective of the agent is to learn an optimal policy that provides the maximum cumulative discounted rewards subject to the condition that the discounted sum of cumulative costs are less than a threshold beta. In many problems, it is difficult to specify the constraint function manually. Alternatively, it is easier to obtain expert demonstrations from which the constraints can be estimated. For example, in autonomous driving, it is hard to specify all the constraints accurately. Rather, it is easier to obtain demonstrations from expert drivers. Inverse constraint reinforcement learning, or ICRL, estimates the constraint function and optionally also the reward function from expert data in such a way that when CRL is performed with the estimated constraints and rewards, the optimal policy represents the behavior in the expert dataset. In our work, we will assume that the reward function is provided and the agent only estimates the constraint function from the expert dataset. This work is on confidence-aware inverse constraint reinforcement learning, where the intuition is that more expert trajectories adhering to a constraint implies higher confidence in that constraint. Practitioners usually have a notion of confidence with which they would like to accept or reject the constraint learned from data. Prior work did not provide a way to maintain confidence in the estimated constraints. Our work provides a novel ICRL algorithm called confidence-aware ICRL or CAICRL. CAICRL is capable of maintaining confidence measures in the estimated constraints. In our work, we studied two use cases using CAICRL. The first is inferring constraints based on the provided confidence. The second is determining sufficiency of expert trajectories based on the desired performance and confidence. This slide captures the differences in approaches of ICRL and CAICRL. The ICRL shown on the left-hand side has two alternating steps where the policy is updated in the forward step and the constraint is estimated in the inverse step. In ICRL, the constraints are typically point estimates. Alternatively, the CAICRL algorithm maintains a constraint distribution which is adjusted in the inverse step. After the inverse step, the constraints are estimated based on the constraint distribution and the required confidence measure denoted by lambda. In the first case, we study the problem of inferring a constraint conditioned on a provided confidence. Here, we use a beta distribution to model the constraint distribution. This is represented by a neural network having multiple encoded blocks with shared weights. The three steps involved in CAICRL is captured in the figure on the left, and the neural network architecture of the beta distribution is captured by the figure on the right. In the second case, we provide a method that determines if the number of expert trajectories are sufficient based on the confidence and the performance requirements. Intuitively, having less expert trajectories would lead to the algorithm learning more constraining constraints, which leads to less performances. The flow diagram in this slide shows an approach where more expert trajectories could be obtained if the performance requirements represented by delta are not met with the current set of expert trajectories and the confidence lambda. We conduct an elaborate set of experiments covering multiple domains. We use 5 robotic domains, which are modifications of the well-known Mujoko environments. Further, we use 2 real-world domains where data comes from realistic high-D driving datasets. We perform extensive comparisons to a set of 4 state-of-the-art baselines, BC2L, GACL, ICRL, and BICRL. We use constraint violation rate and reward obtained as performance measures, where we want algorithms to obtain high rewards with low constraint violation rates. This slide captures the performances of CAICRL and all the baselines on the Mujoko robotic environments. CAICRL uses a confidence measure of 0.7. Across all the domains, CAICRL shows higher rewards and lower constraint violation rates as compared to the baselines. Further, we can observe that the constraint violation rate for CAICRL stays below 0.3 for most experiments, showing that it is able to learn constraints which are at least as constraining as the ground truth constraints with a desired confidence. In this slide, we show the second case where CAICRL can be used to determine if the number of expert trajectories are sufficient or not. We choose the blocked Walker environment where we vary the number of expert trajectories from 100 to 300. As the number of expert trajectories increases, we notice that the performance in terms of rewards keeps increasing. In all the three cases, we notice that the constraint violation rate stays below 0.2, corresponding with the confidence requirement of 80% for CAICRO. To conclude, in this paper, we provide an algorithm called CAICRO that introduces a notion of confidence in ICRO. We consider two use cases where CAICRO is used to infer constraints with a desired confidence, and the second use case corresponds to determining the sufficiency of expert trajectories based on the desired confidence and performance requirements. We provided extensive experiments that showcase the advantages of CAICRO as compared to state-of-the-art baselines in robotics and driving domains. Thank you for your interest in our work. This slide has links to the paper and the code. It also contains my contact details for any questions or comments.